Hello, everybody. Welcome to lesson 7.3 for Math 9. So, we're going to talk about similar polygons. If you missed lesson 7.2, you need to go back to 7.2 because we're going to be talking about scales and stuff like that. So, 7.2 is about enlargements, that's making shapes bigger, and reductions, that's making things smaller. Beautiful. Today we're going to talk about similar polygons. Similar polygons means that you have two shapes that are the same, but they are bigger or smaller. And they've gotten bigger or smaller in the same ratio or the same scale. So, for instance, if you look at these two shapes, they're similar shapes because their angles haven't changed. That means that the side lengths have all grown at the same ratio. So you'll notice here, like at R, I have an angle of 96. I still have an angle of 96. At Q, I have an angle of 104. I still have an angle of 154. I still have my 90 degrees in the corners, just like in both shapes. And then I still have an angle of 110 degrees coming out of S. So when the angles don't change, you have similar polygons. It also means that your side lengths have all grown or shrunk by the same scale, which is what we talked about in lesson 7.2, growing side lengths by the scale factor. Sometimes our shapes are going to be flipped around. You're going to see examples of that, and you're going to have a little bit of a harder time than just looking like we did right now to be like, yeah, those are similar. Let's just start to get into it. So if we look, RS. So RS means from point R right here to point S right here. That's 2.5. If you look at side length ST, so ST means if you drew a dot at S, you drew a dot at T, and you connected the dots, that's 2.5. TP is across the bottom, so that would be 3. PQ is on the left side, which is 2, and then from Q to R is 1.5. Perfect. We want to figure out the corresponding side length. So that means it's the same side length, but on my bigger object. So for instance, from R to S would be from R prime to S prime. This right here on my new object to this right here on my new object. And that is now 3.75. If you look at ST on my corresponding corners, that's S prime to T prime, and that's 3.75. If you look at TP, that is now T prime, P prime, which is 4.5. If you look at PQ, that is now on my new triangle, corner P prime to Q prime. That's 3 centimeters on my new shape. And if I look at QR, that matches up with Q prime to R prime, which on my new shape is 2.25. Beautiful. Okay, the scale factors. So to calculate the scale factor that something has grown or shrunk, what you want to do is you want to do the new length divided by the old length. So for us, if I wanted to know the scale factor that RS grew by, I would do 3.75 divided by 2. And if I put that in my calculator, that'll tell me my scale factor, which equals 1.875. Awesome. And I can do that for all these lengths. So I'm going to take the new length and divide by the old length for all these corresponding side lengths. So this one would be 3.75 divided by 2. It also equals 1.875. If I look at from TP, I go 4.5 divided by 3. It equals 1.5. If I look at, wait, something's wrong. You probably noticed it's not 2, it's 2.5. I knew something was wrong because my scale factors should all match because these were similar. triangles or similar shapes. Yep, there we go. These should all be 1.5, not 1.875. Most of you probably caught my mistake while I was doing it, and now you're like, oh, Mr. Kennedy, you've wasted my time. But that's okay. Sometimes you need to waste your time when you're in quarantine. Otherwise, you're just going back to what? Twiddling your thumbs and being bored? All right, so if we keep going, we would do our old, which was 3 divided by our new, which is 2, which equals a scale factor of 1.5. If you look at your last one here, we have 2.25 divided by 1.5. That's a scale factor of 1.5. Beautiful. I'm going to double check that that is right in my calculator. It is. It's 1.5. When you have a shape where all scale factors are the same, and if you look, these are all the same scale factors, that means you have similar shapes. If even one of those wasn't the same, then you don't have similar shapes. It would actually distort the way that the thing looks. So one of the sides would be too long or too short or something like that. Another way to check if you have similar shapes is to look at the angles. So for instance, if we look up here, the way that this reads as angle P. That means you want to look and figure out where corner P is. It's right there. And figure out the angle that's at that point. In our case, it's 90 degrees. And that matches up with angle P prime over here, which if you look is also 90 degrees. When you have similar shapes, you're actually going to notice that all the angles are the same when you look from one shape to the new shape. So angle Q is 154. That means angle Q prime is also 154. Angle R is 96. That means angle R prime is also 96 degrees. Angle S is 110 degrees. That means angle S prime is also 110 degrees. And if you look at angle T, that's 90 degrees. That means angle T prime is also 90 degrees. When all the angles match the way that we have here, so all my angles match, that tells me I have similar shapes. If even one angle didn't properly match up, then I wouldn't have a similar shape anymore. The change in angle would change the length of one of the side lengths that are coming out of that angle. So that's what we're going to be working off of today. This idea that to have a similar shape means that you must be growing or shrinking the length size by the same scale factor. And it also means that your angles must be the exact same. Awesome. Let's look at this right here. So we have to determine if these quadrilaterals, that means four-sided shape, are similar. So are they similar? The way I can check is to see if the side lengths have all grown by the same ratio or the same scale. So the first thing first, I need to figure out which sides match up. So if I'm looking at these sides right here, I would say that blue side is the same as this blue side over here. I'd say those are the sides that match up. And if you notice, like right across from it, those are also the same. Beautiful. The other sides that match up would be across the bottom and the top. And if I'm looking at my transform shape, it'd be the bottom over here and the top over here. Okay, there's a problem. The problem is if I look at my original shape and I look at the length and the width, my length, we're going to say is 35, and my width is 30. That means this is bigger and this side is smaller. If I look at my transform shape on the right, it's actually not that way because 18 is smaller and 21 is bigger. So the way that I've matched up these shapes with their line colors is actually wrong. So the shape has shrunk, right? I can clearly tell that that quadrilateral or that rectangle has gotten smaller, but it's actually also spun itself. So to match up properly, I need to recognize that they've turned this shape as well. And the sides that match up are actually the opposites. So the red sides are now on the side, and the blue sides are now on the top and bottom. They've turned the shape. If we use letters to recognize the corners, so maybe this will help too. If I say this is corner A, B, C, D, they've now turned it so that A is down here, B is over here, C is over here, and D is over there. They've turned the shape. And I'm going to use like A prime, B prime, C prime, D prime, just with a little apostrophe. That means like it's the new side or the new corner. Okay, we've now figured out which sides correspond with which sides, like where they match up. Now I have to figure out, are the scales the same? Did it grow and shrink at the same rate? I'm going to compare AB scale and compare it to what happened to the new AB. So A prime to B prime. The way I do that is by doing the old and dividing by the new. When I do the old AB, it's 30. When I do the new AB, it's 18. If I put that in my calculator, oh, sorry. I said old over new. It's new over old. I'm so sorry. I've had 2 coffees today. Like, you think life would be good, but here I am making simple mistakes. New over old. There we go. My new AB is 18. My old AB is 30. If I put that on my calculator, 18 divided by 30, I get 0.6. If these are similar triangles or similar quadrilaterals, that means that when I check my other side length, it should also grow by a scale of 0.6. So that means if I was to take, for instance, B to C, it should be the same scale as B prime to C prime. Again, we're going to do new divided by old. So I'm going to take B prime to C prime, which is 21. I'm going to divide it by the old B to C, which is 35. If I put that in my calculator, 21 divided by 35, sure enough, is 0.6. These are the same. That means, yes, they are similar. They're similar because the rate at which they grew was the same. Right? That's how you know. If we look at question B, the first thing I want to do is make sure I'm matching up the sides properly. This one's pretty easy to tell that it's properly set up. So the longest side is the top. If I look over here, the longest side is still the top. That's good news. If I look at the bottom, that should be my shortest side. And again, it is the shortest side. The third side that we have is these side lengths. They're going at the same angle and matching up over there. To check if these are the same, that means that if I was to label these corners A, B, C, D, and A prime, B prime, C prime, D prime, that all the ratios or all the scales should also be the same. That means A prime, B prime, that's the new, divided by the old AB, should equal my B prime to C prime divided by my B to C, which should equal my C prime D prime divided by my CD, which should equal from A to D divided by A prime D prime. Essentially, what I'm saying is all the lengths should have the same scale factor. They should all grow or shrink by the same rate. And we're going to try that out. So if you look, we're going to do what color is that? A prime to B prime divided by AB. So that would be 9.4 divided by 17.3. If you put that in your calculator, 9.4 divided by 17.3 equals 0.543. If I do another side length, so let's do 18. I'll do this one in red because that's the bottom side is in red. So the bottom would be, the new one is 18, the old one is 29. If I put that in my calculator, 18 divided by 29 equals 0.621. And you will notice that these scale factors are not the same. Since the scale factors are not equal, that means that those sides did not grow at the same rate. That means these things are not similar. One was growing faster than the other or shrinking faster than the other, depending on how you want to look at these pictures. Perfect. If you look at this shape, we have two sides. So we have the sides of these shapes right here in blue. They match up with the sides over here in blue. If I look at the tops match up nicely. If I look at the bottoms clearly match up nicely. If I wanted to see if these things are similar, that means the sides should have been shrinking at the same rate that the top and bottom were shrinking, meaning that they must have the same scale factor. You want to do new divided by old. My new length is 40 on the side divided by my old length of 48. That tells me that the scale factor that the sides grew at was 0.83 repeated. If I want to check the tops and bottoms, it would be 20 new divided by old, 24. You put that in your calculator and you get 0.83 repeated. That means the top bottom grew at the same rate as the two sides. These are the same. If the scale factor is the same, you have similar shapes. Beautiful. That's all similar shapes are. Are things growing and shrinking at the same rate? They all have to grow and shrink at the same rate, every side length. If one of them is different, then they're not similar. Perfect. We could also use this idea of scale factors to help us figure out missing side lengths. So for instance, they said in the polygons in each pair are similar. They told us each pair are similar. If they're similar, that means they're the same scale. They're growing and shrinking at the same rate. Determine the missing side. So we look over here. I have the shape on the right. The top and the bottom are both 15. The side is 24. In the other shape, they've told me the top is 10. That means the bottom must also be 10. And they want to know what is the side. That's how they put a question mark there. Before I can figure out what that missing side length is, I have to figure out how this thing is growing. That's called the scale. So how is it being scaled? To figure out the scale, you take the new and you divide it by the old. If we were to do that with this shape, the new top is 15. The old top is 10. Put that in your calculator. 1.5 is your scale. Then I can use that scale to figure out what my missing side is. To do that, you use our formula, which would be your old, that looks like DD. You take your old side, you multiply it by your scale, and it equals your new side. For us, our old, we don't know what our old is, so we call it x. Multiply by our scale, we calculate our scale to be 1.5. And that should now equal your new side length. Your new side length is 24. Your goal was to figure out what the old side was, which I've called x. The way I do that is by getting x by itself. So I'm actually going to divide both sides by 1.5. That tells me that x, or my old side length, 24 divided by 1.5, was 16. My missing side was 16. So just to review, we had two shapes. We had to figure out the scale of the shapes, how it was growing. We then took that scale and put it into this little formula right here that helps me calculate side lengths. So the formula was old times your scale will equal your new. We were looking for old, so that means we actually had to divide our scale to the other side, and that told us that x equals 16. Cool. Let's try this again. So we look over here. We've got these two shapes. You can tell that they're similar. It told us it's similar, which is nice, but you can also tell that it's been rotated. So it's actually been flipped around. That shouldn't make a difference. This is this side right here. Oh, sorry, I wanted to do it in a different color. This side right here and this side right here on the shape are actually the same as these two right here. Perfect. The other sides, top and bottom, are still the top and bottom. The shape has just been flipped, so they've rotated it around. Okay. If I want to figure out the new green side, this one right here, because that's what I'm looking for, I have to take the old and multiply it by the scale, and that would tell me my new. I can't do that unless I know what the scale is. To calculate the scale, you have to work with side lengths that you do know. I know that my new top is 12. If I divide that by my old top of 6, that would give me a scale of 2. Then I can do my calculation of old, which is 5, times my scale, which is 2. That would tell me my new side. 5 times 2 is 10. So 10 is my new missing side length. Perfect. Similar triangles. Similar triangles is the same idea as similar shapes or polygons that we did above. It means that the side lengths have grown or shrunk by the same. It also means that the angles are the same. Similar triangles are not congruent. That might be a word you've heard before. Congruent means that the side lengths are the same. These side lengths change. It's grown or shrunk. So they're only similar triangles. They are not the same triangles. They're not congruent. Just in case you've ever heard the word congruent and you're like, oh, what the heck's going on? You'll notice that they've got these two triangles over here. So they're trying to demonstrate that like the angles have stayed the same. So angle C right there, the smiley face, matches up with angle F over here. If I look up here, I got the big solid dot. That should match up with my big solid dot over there. And then I've got my angle star over here. That means it's equal to this angle star over there. Also allows us to understand that C and F must actually be corresponding to each other. That means they're connected. A and D have connected somehow, right? They've either something has happened to A to turn it into D, and B and E are somehow connected as well. Beautiful. Let's just jump into a triangle question. So we look here. They want us to figure out the missing sides. I'm going to figure out which ones connect. Looking at these triangles, 7.5 and x are connected. They're somehow corresponding to each other. 6 and 12 are somehow connected or corresponded through the bottom. And then y and 8 are somehow connected. Our job is to figure out what x and y are. So how did my triangle grow or shrink to become x and y? The only way you can do this is by calculating the scale. And the way you calculate the scale is by taking a new side and dividing by an old side. The only sides that match where I knew both numbers was my red. So that means my new one of 12 divided by my old one of 6 would tell me that the scale is 2. Then I can use that scale to calculate new lengths. We'll start with x. So if I had 7.5, actually I'm going to write out the formula first. Old times scale equals new. So if I took my old length of 7.5, I multiplied by my scale of 2, that would give me my matching side length of x. I put that in my calculator. 7.5 times 2 is 15. That means 15 is x. If I want to figure out what y is, y was actually my old, and then multiply by my scale of 2, and that will equal my new side of 8. I have to get y by itself. That means I have to divide both sides by 2. That means my y length equals 4. Y is 4. And that's how you figure out missing side lengths. Just like the questions above, except now it's triangles. That's the only difference. It all comes down to calculating scales and then using the scales in your little formula of old times scale equals new. Okay, let's look at this. This right here might be new text for you, something you haven't seen before. That means they're similar. That is similar. So that says triangle ABC is similar to triangle DEF. That means somehow it's grown or shrunk. The first thing we want to do is match up sides, figure out which sides correspond to each other. I think it's pretty safe to say that the bottoms correspond to each other, so 24 and 8 must correspond. Looking at the angles and everything else, it's probably also pretty safe to say 15 and F correspond. And it's also probably pretty safe to say A and 7 correspond. If I want to find missing sides, the very first thing I have to calculate is my scale. Without my scale, I can't do anything. So my scale is like probably the number one most important thing to calculate. My scale equals my new divided by my old. I have to use two numbers that match up. The only ones that match up where I knew numbers for both of them is my red ones, the bottom. And my new bottom is 8, and my old bottom is 24. If I throw that in my calculator, you should get 0.3 repeated. That now tells me my scale. Using my scale, I can do the formula old times scale equals new. Let's try to calculate F first. That means if I took 15 and I multiplied it by my scale of 0.3 repeated, it should equal my new side length F. If you do that, 15 times 0.333333, and you're going to have to put all those threes in your calculator, I end up getting 5 equals F. And that gives me one of my new side lengths. For my green one, my old was A times my scale of 0.3 repeated. That equals my new side length in green, which is 7. I'm going to have to divide both sides by 0.3 repeated in order to get A by itself. When I do that, I get A equals, and then 7 divided by 0.33333333 equals 21. That means my side A must have been 21. Awesome. So that's what we're doing. We're finding the scale, then we're using the scale and applying it to the triangles to figure out which sides match up. I want you to go ahead and see if you can do these questions. Sometimes it's hard to see where the similar triangles are. Let's start with just A. So try to see if you can do A, find the missing side of X, and see if you can do that. Then unpause, watch me explain it. If you got it right, awesome. Then you can even give B a try, C and D a try. But those ones are definitely harder to see where the triangles are similar. But you can try it. Okay, so hopefully you attempted this. I'm just going to draw colors so you can kind of see which sides match up with which sides. Looking at this, they told me which angles match up, so that might help me figure out which sides are which sides. But you should have got that 8.4 matches up with X, which is what we're looking for, and that my side length of 3.5 matched up with my side length of 5, which is kind of nice. It's the only numbers they gave you. So that makes it pretty simple. If I'm trying to find a missing side, the first thing I have to do is figure out what my scale is. To figure out the scale, I want to do my new side divided by my old side for one of my matching pairs. My blue ones match. My new side is 3.5. My old side was 5. If I throw that in my calculator, I will get that my scale is changing at a 0.7 rate. Now with that info, I can go to my formula, which was my old side times my scale equals my new side. I don't know what the old side is when I look at my reds because my old side is what X is. So X times my scale of 0.7 equals my new side of 8.4. To get X by itself, I have to divide that 0.7 to the other side. When I do 8.4 divided by 0.7, 8.4 divided by 0.7 gives me 12 as my original side. So my answer for this triangle would have been that X equals 12. Awesome. Let's look over here. So if you look at this, these are two triangles that are actually similar triangles, even though it might be kind of hard to tell. Luckily, the only sides that really match up here is these two are obvious, right? They're obviously 4 and 14 are the top and the bottom. They're supposed to match. And then we have X over here and 5 over here. These sides actually match up. The way that I know these sides match up is by looking at their angles. So I got this angle in here matches this angle in here. And then when I have something like this angle here, it matches across from it like that. That allows me to see that, okay, this angle opens up to X, this angle opens up to 5. Regardless, if you tried this question, you have to find your scale first. I'm going to say I went from the top to the bottom. So my new side would be 14. My old would be 4. If I throw that in my calculator, 14 divided by 4, I get a scale of 3.5. Not skate, scale. There we go. With my scale, I can then do my little math trick of old times scale equals new. So for us, our old side was 5 multiplied by a scale of 3.5. It'd give me my new X length of X. So 5 times 3.5 is 17.5 equals X. That tells me my missing side. Awesome. We have 2 more down here. If you want to try them on your own, go ahead. I'll show you where the 2 triangles are. So we have a triangle here. And that triangle is similar to the bigger triangle that's kind of around it, this one right here. Like that. So if I'm trying to compare similar sides, I would have to recognize that these left sides, 4 and Z, are the same. And then the bottoms, 6 and 10, are the same. The only way I'm going to be able to figure out Z is if I figure out my scale. My scale is my new divided by my old. I'm going to say that my new on my red is 10. My old is 6. If I throw that on my calculator, 10 divided by 6, that gives me 1.6 repeated. You have to put in all those sixes, so you go 1.666 when you're using it. I then want to use So now if I want to use that scale, I need to use my trick of the old side times the scale equals the new side. My old side, if I'm looking at that, would have been 4. Then I would have multiplied by my scale of 1.6 repeated, and that would give me my new side of z. We do that 4 times 1.6666, and you should get that 6.6 repeated is my new side length. That little line above the 6 means that 6 goes on forever repeating. Wonderful. Our last one on this page over here. Again, we have like a triangle inside of a triangle. So we have this one right here. And we have a bigger one around it right here. If I'm matching up my sides, this would mean that 3.5 and x would be matched up. And it means that my 7 and my 8 would be matched up. I'm going to pretend that I went from the smaller triangle to the bigger triangle. So that means I want to figure out the scale first. To calculate the scale, you do new divided by old. My new side is going to be 8. My old side is going to be 7. Put that in my calculator, 8 divided by 7. And I get a really bad number, 1.1428. And then I just run out of space, ... I'm going to use all those decimals later on. To calculate my missing side, I have to use my formula of the old times the scale will equal the new. I'm pretending that my small triangle was the old, so that means I had 3.5. I multiply it by my scale of 8 divided by 7, and that should equal my new side, which is x. If I do that, I put that in my calculator. So 3.5 times 1.142857143, or if you use the fraction 8 over 7, that's fine too. You should get that 4 equals your new side. So that's how much it grew by, 4. Sorry, that's what it grew to become, is 4. Fantastic. We have 2 word problems here, so you can kind of see how scale could apply to something. The first thing with word problems is I definitely want to read it, try to pick out any information that matters. On the plus side, there's 2 diagrams already drawn for us. Sometimes you might have to draw the diagram. After I read it is typically when I reread it and then try to draw the diagram or write out any information that's necessary. If I look at this, it says at a certain time of day, a person 1.8 meters tall has a shadow 1.3 meters long. At the same time, the shadow of a totem pole is 6 meters long. The sun's rays interact with the ground at equal angles. So the angles are equal. That tells us right away when my angles are equal, that means I have similar triangles. That means that they should be growing at the same scale or shrinking at the same scale, and we can use that to help us figure anything out. How tall is the totem pole to the nearest tenth of a meter? Okay. How tall is the totem pole? I like to call that x. So what I'm looking for on my picture over here is that height of the totem pole, which is x. I want to match that up with my triangle over here to see which side is the same. I would say that the height of the person is corresponding to the height of my totem pole. So x matches up with 1.8. I would also look at my drawing and notice that the shadows would correspond with each other. So the shadow of the totem pole is 6. The shadow of the human is 1.3. Those 2 things correspond with each other. Our goal is to somehow use similar triangles to figure out the height of that totem pole. To do that, I need to calculate my scale. Scale, in case you forgot, equals your new divided by our old. I'm going to pretend that the human is the old triangle, the totem pole is the new triangle. So our scale for this one would be 6 divided by 1.3. That means my scale is 4.61538, and then ... That is my scale. By calculating my scale, I can then apply it using my formula of old times scale equals new. My old length was 1.3. Times that by my scale of 6 divided by 1.3. And it should equal your new height. I made a typo there. I typed 1.3, should be 1.8 is the old height of the human. There we go. 1.8 times my scale of 6 over 1.3. We multiply those two things together. That should give me my new height. We're going to round to the nearest tenth of a meter because that's what it told us to do. So that's one decimal place. My answer is 8.3 equals my new side length or my totem pole, which is x. So 8.3 is the answer. Again, just like all the previous questions, find out what the scale is by calculating new divided by old, and then use the scale by multiplying it by the old length or the old triangle's length. We have one more question here. I want you to give it a try on your own. See if you can match up which sides match with which sides. See if you can actually calculate what it's asking you to calculate. Then unpause and see if you did it right. Okay, hopefully you did that. Hopefully you paused and then did it and then unpaused. It says a surveyor used the scale diagram to determine the width of the river. Determine the width of the river AB. AB means if you went from A, which is right here, and you drew a line to B, which is right here, which happens to be the width of the river, right? And I call it X because that's what I'm looking for. Determine the width of the river AB to the nearest tenth of a meter. The only way I'm going to be able to do this is with similar triangles, and I have to figure out which sides correspond to which sides. Looking at this, they've told you that this angle right here is the same as this angle right there, which means that whatever's across from those angles, 98.3 and X, are corresponding, and then whatever's right next to those angles, 73.2 and 28.9, are corresponding. We can use those corresponding side lengths, the blue ones, to calculate my length. I'm going to say that my old triangle is the 28.9 and my new triangle is the 73.2. It doesn't matter which one you call new, which one you call old, as long as you just keep it consistent. So I'm going to say that the small one is the old and the big one is the new. If I want to calculate my scale using those two corresponding sides, I do the new side divided by the old side. My new triangle is 73.2. My old triangle is 28.9. This gives me a scale, 28.9, of 2.5328, so on and so forth. I then use that scale by doing old side length times the scale equals the new side length. My old is X, because I called my little one my old triangle. I then multiply that by my scale, which was 2.5328. And that should equal my new side length, which on our big triangle, that was 98.3. We have to somehow get X by itself, so we divide both sides by 2.5328. And I am using all those decimals. I'm just only writing out the first four. So I divide by 2.5328, ... I put that in my calculator, 98.3 divided by 2.532871,972. And I get that my distance X, which is the width across the river, equals 38.8 if I round to the nearest tenth of a meter. That is my final answer. Hopefully you enjoyed learning about scales and similar triangles and polygons and rectangles and all the fun things in the world, and it kept you entertained a little bit during this wonderful quarantine where I'm sure you are bored out of your mind. All right, we'll see you soon. Take care.